Sudbury, of course, has been mentioned facetiously in connection with the moon by many people in many jokes for a long time. But there are real geological reasons for associating Sudbury with the moon, and I'll leave you to watch the program, which is a full hour of the moon and Sudbury. Moon. Curiously enough, at the same time that we were racing to the moon, other geologists were racing to the parts of the Earth which are still least known, the deepest parts of the oceans. There was a race going on, in fact, to learn about our own planet, as well as a race to learn about our moon. Sudbury, of course, has been mentioned facetiously in connection with the moon by many people in many jokes for a long time. But there are real geological reasons for associating Sudbury with the moon, and I'll leave you to watch the program, which is a full hour of the moon and Sudbury. Long before men landed on the moon and began to explore its surface and probe its interior with seismic shock experiments, many scientists had speculated that the moon would yield evidence about the events which occurred in the early history of this part of the solar system. On the Earth, these events have left no record because during the last 2.5 billion years, they've been obliterated by the activities of plate tectonics, by mountain building, and by the drifting apart of continents and the creation of oceans, for example. Those expectations have been amply fulfilled. And the purpose of this program is to look at some of the conclusions which scientists have been able to draw from the almost 3/4 of a ton of rock samples, the many, many thousands of photographs, and also the vast quantity of data which has been gathered by a variety of experiments during the last 6 or 7 years. We'll also look very briefly at the real reason why Sudbury has a special place in the hearts of at least 2 Apollo crews. You may remember that the Apollo 16 and Apollo 17 crews, the men who were subsequently to walk on the moon, visited and trained in the Sudbury area. Much of the work to be done on the moon is geological, and the astronauts were going to be looking at the remains of rocks which had been impacted by meteorites. Many geologists believe that the Sudbury Basin is a meteorite crater, and it's for this reason that the Apollo 16 crew, complete with equipment, came here in 1971, and in 1972, the Apollo 17 crew, without their equipment, concentrated on the geology here, for example, at the Onaping Falls. Jack Schmitt, the geologist who was to be on the Apollo 17 crew, was already familiar with the kind of geology to be found in the Sudbury area. The resemblance of Sudbury to the moon has a great deal more to do with its very, very interesting geology than with its scenery. But to the origin of the moon. One of the first theories regarding the origin of the moon was that the moon had been derived or broken away from the Earth, and that the Pacific Ocean, in fact, was a scar that was left. That theory has been rejected for a variety of reasons, because when tested, for example, against the chemistry and the knowledge of the density of the moon and the Earth, it simply doesn't fit. Dr. Harold Urey has been one of the most prominent persons concerned in the development of the ideas on the origin and development of the moon, and many of his ideas have stood the test of the Apollo data. In this short film extract of a talk that he gave in 1972, he explains why he rejects the suggestion that the moon broke away from the Earth.
The moon is an odd object in this array. It consists of about 1/200th of the total mass of the terrestrial planets and is a very odd object, not like the others at all. It was suggested by Sir George Darwin that the moon escaped from the Earth. This was made in order to account for its density. If the moon escaped from the Earth, it should be a part of the outer part of the Earth, which has a low density, and would not contain much of the core, at least, which has a high density. This has proved to be difficult to accept, because the space program has developed the chemistry of the moon in much greater detail. In the first place, it contains some very high boiling silicate materials. There's a lot of aluminum, calcium silicate, for example, known as Unorthosite, in the outer parts of the moon. There's also some basalt and other things, but no granite has been observed. In addition to that, it contains little of certain volatile elements. For example, potassium has a low abundance relative to uranium. The potassium to uranium ratio in the moon is about 2,000 to 1, whereas in the Earth it's 10,000 to 1. In the meteorite, 60,000 to 1 or something like that. It does not seem possible that we could skim off a layer off the surface of the Earth and put it into the moon and meet these chemical conditions. It does not seem probable or even possible that the moon escaped from the Earth. One of the physical facts of gases is often overlooked. If I compress a gas, it will then expand back again. This is well known. But one that isn't so well known is this, that if I have a large mass of gas and I compress it, I get an increased amount of matter in the part that is compressed, and that has a gravitational field that attracts the material around it. And as a result of this, if it gets large enough, it will not expand again. It will snap off and become a gas sphere. And I have been led to believe by very competent people in the field that a solar nebula would be gravitationally unstable. And if it is gravitationally unstable, one will have gas spheres of some kind or other formed as a result of this. If one fixes the density of the gas and its temperature just right, it will be large enough to produce a moon. Professor Runcorn and I thought possibly that the moon has a cold core instead of a hot core. We thought probably the moon accumulated at low temperatures with small particles containing a little iron, falling through a cold gas and forming a sphere of solid material at low temperatures. Of course, magnetic particles falling like this in the presence of a magnetic field would become more or less oriented. And when we get through, we would have a nice magnet, great big magnet, say going out to half of the radius of the moon. It would then have heated up due to radioactivity in the material, and as a result, it would get above what is called the Curie point, named after the Curies, which for iron is 780 degrees centigrade. And then the magnetic field escapes and would disappear and would be just what we observe at the present time.
Dr. Urey rejected the moon as having been derived from the Earth because of differences in the chemical composition between the two planets. But those same chemical differences are also a problem which arises if the moon originated by the accumulation of fragments in a cold gas cloud at the same time as the Earth and the other planets, as Dr. Urey explains in a continuation of that same talk.
Is it possible that the moon is indeed a primitive object. Did it get made from solar material while it was distributed in a disk about the sun? And did many other moons of this kind get made by a similar process at the same time? Well, there is a difficulty about the iron abundance. The abundance of iron in the moon must be about 10-15%, whereas the present ideas about the abundance of iron in the sun would make material of the kind of the moon having a density of about 3.8 or something like that, and an abundance of iron of about 30-35% like the Earth. If the moon is indeed a primitive object with a low abundance of iron in its makeup, we have to make planets that contain considerably more iron. And whatever else is true, it looks very much as though we must make at least Mercury with a greatly increased proportion of metallic iron in order to get its high density. So this is a problem that faces us in any case. I have thought that possibly after the moons were formed in gas spheres, the gas was blown away by a T Tauri star. That is a star that has an enormous burst of energy, possibly due to deuterium burning, which blows the gases away. And we have then a bunch of lunar-type objects about that size colliding with each other and make a mess of finely divided silicate and rather larger metallic iron objects about, and that solar wind of a more vigorous type than we have at the present time blew some of the silicate materials into space and left behind a higher concentration of metallic iron. And then this accumulated into the Earth. And there is again a difficulty. We have to worry about why was it not accumulated into the moon and give us a high density moon. And I do not know the answer to these problems in a satisfactory way at all.
Despite the difficulties mentioned by Dr. Urey, the suggestion that the moon accumulated by the agglomeration of fragments in a gas cloud is now the most widely held theory for the origin of the moon. We do know that the moon probably originated in the same area of the solar system as the Earth, and we know this because of the similarity in the oxygen isotopes. You'll remember that an isotope of an element is an atom that has got a different number of neutrons in the nucleus, the same number of protons, but a different number of neutrons. And there are 3 isotopes of oxygen. An isotope with a total of 16 neutrons and protons, one with 17 and another with 18. And on the Earth, there's a distinctive proportion of these 3 isotopes that's also the same in the moon, in the oxygen-silicon tetrahedra, for example, of the silicate minerals. On the meteorites that reach the Earth from different parts of the solar system, the oxygen isotope ratios, the proportion of the 3 isotopes, is different. So we've got good evidence that the moon and the Earth originated in the same area of the solar system. And this also tends to rule out then the suggestion that the moon was captured by the Earth. That is, it arrived in orbit around the Earth from another area in the solar system. The suggestion that the moon was derived from the Earth, as you've heard Dr. Urey explain, is now not thought to be likely. But there are still geologists and other scientists who believe that the moon might have been derived from the Earth in some complex way in the very early stages of the origin of the solar system. You might well expect that there'd be controversy over the origin of the moon. After all, it's a very complicated matter. But you might expect that the surface features of the moon, such as the very obvious craters, would be the subject of less controversy. But this is not, in fact, the case. The craters on the surface of the moon have been argued over ever since the invention of the telescope. How were they produced? Simple experiments showed that they might have been formed either by volcanic activity or that they might be the scars of meteorite impacts. One of the most prominent craters on the moon is Copernicus, about 2 miles deep and about 60 miles in diameter. Apart from its very large size, Copernicus seems to be typical of most lunar craters, and it shows several of their characteristics very well. In the center of the floor of the crater is a group of central mountains about 1,000 feet high, and its walls are formed by a series of terraces. The outer flanks of the crater have a hummocky or rather lumpy appearance, and small craters dot the area around the main crater. Seen from a distance, a pattern of rays or light-colored streaks extends for several hundred kilometers in all directions. These characteristics have led some scientists to interpret Copernicus as a volcanic caldera like those found on Earth. A volcanic caldera is formed partly from the explosive crater produced by violent volcanic eruptions, and after the eruption by the subsidence back into the magma chamber. So on appearance, Copernicus could be a volcanic caldera like those on Earth. It has central mountains. It has terraces. And it's surrounded by hummocky terrain. The resemblance to volcanic calderas is certainly quite close. On the other hand, meteorite impact craters also resemble Copernicus. This is the best known meteorite impact crater in the world, Meteor Crater in Arizona. It's less than a mile in diameter and was produced by a small meteorite about 100 feet across, about the size of the house on the rim of the crater. Around the rim are hummocks formed by great clots of debris thrown out during the impact. The closest we can get to understanding the effects of an impact of a meteorite are through shallow underground nuclear explosions. The explosions are similar in their effect to that which follows the impact of a meteorite. Material is thrown in all directions, broken up by the friction of the air. Computer models showing exactly what happens during the explosion are also a useful tool in predicting what features one might expect at impact sites, and so perhaps distinguish between volcanic and impact craters. Volcanic and impact. One of the most noticeable features of Copernicus are the so-called rays. And a clue to their origin probably lies in the fact that there are more groups of small craters on the rays than between them. On Earth, fracture zones, such as this one filled by a dike radiating out from an eroded volcano, localize volcanic activity. So the small craters on the rays, like these ones on Earth, could mark localized fractures in the crust of the moon, and the rays could be recent volcanic ash, and therefore light in color. The nuclear explosion crater suggests another possibility. Around the crater are small craters produced by the impact of the great masses of material thrown out of the main crater and broken up in flight. On the moon, where there is no air, these clots will hold together and land with most of their mass intact, thus forming many other small craters. Even the samples brought back from the moon by the first astronauts did not solve the controversy between impact or volcanic action. Many of the rock samples were solidified lava, but in the so-called lunar soil, there were large numbers of tiny glass droplets of a variety of shapes. Under the microscope, they were all seen to be covered by tiny craters, formed by high-speed impacts of very tiny particles, micrometeorites. So there is direct evidence of impacts on a small scale, but can one therefore conclude that there have been large impacts, especially since the glassy spheres themselves are very similar to the volcanic glass droplets from volcanic ash on the Earth? So even the most obvious aspects of the moon are the subject of great controversy. The origin of the moon is discussed with high-powered scientific theories, pro and con. The origin of the craters is also still not certain. Every piece of information that we gain about the moon seems to raise more questions rather than answer questions. In these circumstances, the manned flights to the moon have added a great deal of information which has been very valuable in solving a lot of the puzzles. The latest Apollo flights were those which yielded the best film, and we've culled some shots from 2 of those flights in order to bring back the spirit of those Apollo adventures. Dave Scott, the commander of Apollo 15, had already flown in Gemini 8 and Apollo 9. He would explore the lunar surface with Jim Irwin, while Al Warden, the 3rd member of the crew, the command module pilot, remained in lunar orbit, operating cameras and experiments. The Saturn rocket lifted off on schedule, and apart from a few minor problems, the launch and the 3-day flight toward the moon was uneventful. The usual large crowd watched the launch at the Cape Kennedy Space Center. The landing site chosen for Apollo 15 lay close to the foot of one of the main highland areas of the moon, the Apennine Mountains, which tower about 15,000 feet or 500 meters above the floor of the great flat Mare Imbrium, or Sea of Rains. Their landing site also lay within visiting distance of Hadley Rill, the sinuous lunar canyon about 400 meters deep, which has always been an enigmatic puzzle for lunar observers. The area had been selected by geologists as likely to be one of the most significant and varied geological sites on the moon. Even from their lunar landing craft, Scott and Irwin were able to observe more clearly than ever before the layering produced by successive lunar lava flows on this mountainside called Silver Spur. Many of those lava flows are up to 60 feet thick. It was during the 2nd day of their exploration that Scott and Irwin made perhaps their most significant discovery, when they recognized and collected a fragment of the rock of the lunar highlands. Rock samples brought back by earlier flights had included basalts, produced by volcanic action, and breccias caused by impact. But Scott and Irwin's Unorthosite, the light-colored rock, because of its richness in plagioclase feldspar, was the first sample of its kind. It was the star exhibit of the Apollo 15 flight. The Apollo 15 astronauts landed just about here. The highland area is light-colored, and the dark area is the margin of the Mare Imbrium. The Unorthosite, which was collected by the Apollo 15 crew, had previously, in fact, been found, but only as very small fragments in breccia. Theirs was the first hand specimen of Unorthosite which had been found by the astronauts. The Apollo 16 crew were the crew which first visited Sudbury in 1971, and their successors, the Apollo 17 crew, you'll remember, were also here, and their flight yielded some very splendid and sometimes rather amusing film. The launching of Apollo 17 took place on the evening of December the 6th, 1972. Eugene Cernan, the crew commander, had already orbited the moon as commander of Apollo 7. Although this was the last Apollo flight, it was the first on which a professional scientist had flown. Dr. Harrison, or Jack Schmitt, was trained as a geologist in California and then in Harvard. Schmitt and Cernan were to be the last two Apollo astronauts to sample the lunar surface, but as always, much of the work was to be done by the unsung hero of the command module, the pilot, Ron Evans, who would remain in orbit around the moon with his batteries of cameras and experiments. With the countdown completed, the Saturn rocket generated its 7.5 million pounds of thrust.
Houston, you are go for orbit. Go for orbit. Those are kind words, Robert. We're go for orbit here.
Once in Earth orbit, the astronauts checked out the craft and then began the complex maneuvers which freed the command module and the lunar landing craft from the boosters of the Saturn rocket. After the 3-day coast to the moon, the rather ungainly-looking lunar landing craft parted company from the command module to begin its descent to the surface of the moon, Ron Evans remaining in the command module to orbit the moon for 3 more days. In a preliminary orbit, with the command module beneath them in the distance, the astronauts passed over their landing place, a flat valley in an area called Taurus Littoral, where they would look for young lunar rocks and signs of volcanic activity. The landing on the valley floor was one of the most accurate of the Apollo program, the dust flying as the astronauts inched toward the surface.
Contact. Stop push. Engine stop. Okay, Houston, the Challenger has landed. Roger, Challenger, that's super. Houston, you can tell America that Challenger is at Taurus Littoral.
First Cernan and then Schmitt left the lunar module to begin their exploration.
As I step off at the surface at Taurus Littoral, we'd like to dedicate the first steps of Apollo 17 to all those who made it possible.
Their first job was to unload equipment, including their rover, the electric car in which they would drive to the exploration sites. They also began setting up the instruments of the automatic laboratory, which would transmit signals back to Earth after they left.
Hey, do you need me, G? No, I'm going to go deploy an ALSEP. Have at it. Okay, Bob, I've got my tools of the trade right here.
Drilling core samples of the so-called lunar soil was one of their first early tasks, as Houston plotted their position. Pulling core was not always, however, as easy as they anticipated.
Yeah, we're out in the Egyptian blanket of Camelot for sure now.
Yeah. Man, it didn't feel like this stuff was that hard. No, I'll get it. I knew there was something I needed to get the jack in over here, other side. Let me put some weight here.
Not going anywhere.
Oh, he's going slowly, though. Very slowly.
I'm going to get this thing out now that I got it. Boys, you know, that's what you call getting down into your work.
29.5. Yeah, it's 29.5 minutes from now, but remember, they left this side a little bit late.
There he is. Okay.
Jim, you better make it clear to Parker that we got to pull out.
Even as the astronauts were urged on to their next stop, scientists were interpreting the first signals of the experiments which had already been put into action.
Well, many parts of the ALSEP are functioning very well. The heat flow experiment is working excellently. It's transmitting back temperature data The cooling down is still cooling down from the drilling process, and in a few hours they should be starting to get true heat flow information.
Let's see if I can't crack the corner and get that contact. See if I can't get it.
Look at the boulders out there.
Despite being on the moon, Cernan and Schmidt were quite clearly not overawed by being the focus of so much scientific attention.
I was rolling on the moon one day in a merry, merry month of December. No, May's the month. May, that's right. May is the year of the month. Oh, what a nice day. Oh, funny, there's not a cloud in the sky, except in the earth. Think that'll stop the dust, that one?
The second day of exploration began with repairs to the rear fender of the rover, which had broken the previous day. In Houston, Apollo 16 Commander John Young had worked that night in a pressure suit trying to find a way to repair the damage. Following his instructions, the astronauts made a new fender, formed from a lunar map molded with tape and held in place with clamps from the Lunar Module telescope. The repair was successful, and the astronauts were no longer bothered by dust as they drove to a series of sampling stations after setting up further experiments in the neighborhood of the lunar module itself.
They're somewhere along this rim where they can see.
But they're dropping, Bill, so they must be coming across some.
We're right where we wanted to be for Station 2, and it looks like a great place. Big blocks, it looks like quite a bit of variety from here. Different colors, anyway. Pretty hard, isn't it? That boulder's gonna roll. Man, that is hard. Just don't stub your toe.
The foreground features are somewhat different, simply because they were farther up onto the hill, I think. But otherwise, that's remarkable.
Powdery, it's obviously very cohesive because the bottom of the core is not smooth; it's very jaggedy and fragmental-like.
Gene's finished with the core tube, then we should be able to go.
If we get that
all of that. Yeah.
No, dadgummit. Jack Schmidt having a few problems.
Of all the stations sampled during the second day, none caused more excitement than the find close to a crater called Shorty.
Oh, hey! There is orange soil. Well, don't move it till I see it. It's all over. Orange! Don't move it till I see it. I've stirred it up with my feet. Hey, it is! I can see it from here. It's orange.
That's the volcanic mix.
Somebody unplugged over.
Fantastic, sports fans. It's trench time. Jack, that is really orange.
I think it's the most exciting we've come across since the beginning of the Apollo program. I believe that it's going to be the most rewarding of all the finds on Apollo.
Light gray material on either side. Oh, man, that's incredible. Say, Gene, we're going to have to... That's incredible. You need to get a down-sun color.
There isn't enough time, Tony, to do it, no matter which way you want to do it. We need more time. We may have to split. We have to split 5 in a little bit.
He's getting about 3 centimeters of wax.
They got to leave at a certain time, regardless of what we got.
With only a limited supply of oxygen and water in the backpacks, the astronauts were bound to a tight schedule. Every minute of their exploration had been carefully planned ahead of time using detailed photographs made by orbiting cameras. Surprise discoveries like the orange soil left the scientists at Houston with tantalizing decisions. In the end, shortage of time always sent Cernan and Schmidt hopping back to their rover and on to the next site, or back to the lunar laboratory to activate experiments.
We'd like you to leave immediately.
Okay. My golly, this time goes fast.
While Cernan and Schmidt had been exploring, Ron Evans in the command module had been taking photographs and operating experiments directed at the moon's surface. After 3 days of observation, he was rejoined by his crewmates.
99, proceeded, 3, 2, 1, ignition. Right away, Houston. Vector good. Ag spot. Pitch over.
Their exploration and scientific work behind them, the astronauts once again became pilots as they guided their lunar landing craft into dock with Ron Evans' command module for the flight back to Earth. They left behind an automatic laboratory which would function for years and several explosive packages to be detonated later in order to map discontinuities in the lunar interior. With them, they brought back 250 pounds of samples as well as a mass of recorded data. Their spot-on splashdown was a fitting climax to the Apollo program. Unfortunately, the orange soil was not what the scientists back at Houston had expected that it might be. They thought it was perhaps produced by the action of watery volcanic gases on the surface material, and that would have been the first indication of water on the surface of the moon. But in fact, the orange soil was a collection of tiny glass spheres that were orange because of their high content of titanium and iron, and those glass spheres were thrown out either by a meteorite impact or by a volcanic explosion. In fact, it turned out about 3.7 billion years ago. And that fact reminds us of something that maybe we forget when we look at the surface of the moon, and that is that there isn't any erosion there. The glass spheres had lain there practically on the surface for nearly 4 billion years without being disturbed. And that's something that we have to remember is very, very different from on the moon than on the Earth, where rain and wind and so forth is constantly wearing down the surface features. But the rocks are what are important on the moon and what can give us a plausible story in the development of the moon. Those rocks are basically of 3 types. There's the Unorthosite, the white rock composed of the plagioclase feldspar we call Anorthite, which you heard Dr. Urey mention, and which was Apollo 15's big find. Then there's the so-called lunar norite, which is a little bit like a gabbro, but misleadingly light in color. And then there's basalt, that we've met before on the Earth, and which on the moon is very similar. And then finally, another kind of rock that's commonly found on the moon, breccia, meteorite or volcanic breccia. This is in fact a sample from Sudbury, and it's one of the main rocks that the astronauts came here to look at. Very similar to the rock on the moon. But the breccia is just an agglomeration of fragments of earlier rocks, and it's these 3, the Unorthosite, the gabbro, and the basalt, which are the fundamental components of the moon, so far as we've been able to examine them. And it's those 3 rocks which give us information about the development of the moon. Now, the examples we have here are obviously not moon rocks. They're Earth equivalents, selected to be quite similar to those on the moon, and they really are extremely similar. This is a thin section of a moon rock. The long crystals are plagioclase, and between them are the pyroxene crystals, both minerals that we know from the Earth. This is a thin section of an Earth equivalent, very similar in appearance. And this is a lunar breccia, and this is a thin section of the Onaping breccia, an Earth breccia. So those rocks are really extremely similar to Earth equivalents, or the moon rocks are extremely similar to Earth equivalents. And we can interpret them by understanding the processes which we know to have created the Earth equivalents. Let's take, for example, first the Unorthosite. This very light-colored igneous rock formed almost solely of light-colored feldspar crystals. Well, we know that Unorthosite results from fractional crystallization, a process that we discussed when we looked at igneous rocks, where within a large body of molten material, early crystals, which are heavy, sink to the bottom to form a distinctive kind of igneous rock. And if there were light crystals, they would float to the top. Now, we know that Unorthosite is formed by a concentration of lightweight and light-colored feldspar crystals in the upper part of a body of molten rock, such as this in the diagram. So we know that Unorthosite results from fractional crystallization of a large body of molten rock. Where do we find Unorthosite? What sort of body of molten rock did the Unorthosite result from? Well, we find Unorthosite in the highland areas of the moon, the light-colored and highly cratered areas of the moon. That's where the Unorthosite is found. There's supplementary evidence for the occurrence of Unorthosite from the satellite observations, or from the observations made from the command module on the Apollo flights, of the X-rays re-emitted from the rocks of the lunar surface after they've been bombarded by X-rays which impact on them from the sun. The elements, silicon and aluminum, emit characteristic X-rays when they're bombarded by those from the sun, which we can read in instruments circulating around the moon. And from this fact, we know that the highland areas show a great richness in aluminum as compared with silicon. And this is typical of Unorthosite. The feldspar, the plagioclase feldspar that makes up the Unorthosite, is rich in aluminum. So we've got that kind of secondary evidence rather than just direct evidence of the fact that the lunar highlands are formed of Unorthosite. We've also got some other evidence, and that is from seismic work. Seismic experiments conducted on the surface of the moon after the astronauts have left. The charges that they leave are detonated, and then the path of the waves are plotted. Those experiments have revealed that there seems to be a shell of about 50 or 60 kilometers thick of Unorthosite, or at least the speed of the seismic waves is the same as it would be if that rock were Unorthosite. So there are good grounds for believing that it is Unorthosite. So the evidence points to there being a continuous shell, a spherical shell of Unorthosite about 60 kilometers thick, forming the upper crust of the moon, and covered in some areas by the gray material that we'll look at in a moment that forms the so-called lunar seas. Now, in what sort of circumstances can we get a 60-kilometer thick continuous shell of Unorthosite that's produced by the fractional crystallization of molten rock? Well, remembering that that Unorthosite cannot have been revealed by erosion, because there isn't much erosion on the surface of the moon, we must look for a continuous layer of molten rock on the surface of the moon. A continuous layer, perhaps 200 kilometers thick, a veritable hellish ocean of white-hot molten rock, from which the Unorthosite, here in orange, resulted by the accumulation of the light crystals, and the heavier crystals forming another layer, and the lower part of the molten material. Here, we've only got a remnant, a thin remnant of the molten material left. Now, why did that occur? What sort of time did it occur? Well, first of all, the time, the age of the Unorthosite. the age of the Unorthosite, which was collected by the Apollo 15 astronauts, and the age of fragments of Unorthosite, which have been found in the lunar breccias, is over 4 billion years, something in the order of 4.1, 4.2, even up to 4.4 billion years in age. This is very, very much older, well over 1 billion years older than anything that we find on the Earth. Our oldest rocks on Earth are something over 3 billion years. And it seems then that the moon, in its very early stages, was covered by a continuous sea of molten rock, and that was about 4 billion years ago. The origin, the cause of that molten rock, well, it's thought that probably the heat for the generation of the molten material was produced by the continuous impact of meteorites, and the energy of those impacts was converted into heat, which melted the surface layer. So those are the first two stages then of lunar history that we can trace through understanding the processes through which Unorthosite results, the generation of a molten layer and the fractional crystallization of a 60-kilometer thick Unorthosite crust. How about the Norite? That's the second of the rocks that we shall look at. Well, Norite is produced by a different kind of process a different kind of igneous process, another one that we've met earlier. We met that kind of process, partial melting, in this kind of situation, where a subducting plate of ocean material became very hot as it descended into the asthenosphere of the Earth, and part of that plate melted to give rise to volcanoes, the volcanoes of island arcs. That's the process of partial melting. We also found it beneath spreading ridges, where molten material is generated that comes up the mid-ocean ridges as the two plates of an ocean spread apart. Now, forget the geological situation, which is applicable only to the Earth, where we have lithospheric plates, and just remember the process. Partial melting, the melting of solid material to give a molten lava, but only the melting of part of that solid material. And it's thought that the Norite might be the product of the partial melting, the melting of part of that Unorthosite crust, which originated about 4 billion years ago on the moon. But what sort of evidence have we got for the distribution of the Norite? Where did it partially melt? In what sort of geological or lunar geological situation did it melt? Well, the evidence for the distribution of the Norite suggests that it occurs in isolated peaks, light-colored, in the dark areas of the moon. For example, here in Oceanus Procellarum, and also in Mare Imbrium. The way that we're able to detect the distribution of the Norite is from the fact that the Norite is very rich in uranium and in thorium and in certain other elements which emit characteristic radiation that once again we're able to plot in the orbiting command module of the Apollo flights. And that's what gives the indication of where the Norite is distributed. And the situation in which the Norite seems to have originated then is by partial melting, here the red indicating the source of the molten material, partial melting of the lower part of the Unorthosite crust of the moon at just about the boundary to where we think there might be some rock of pyroxenite kind of composition formed of pyroxene, and that the Norite flooded up into craters which had been produced in the surface of the Unorthosite crust. And because it flooded up into craters, it's therefore now quite restricted in its distribution, only found in certain areas, which have subsequently been covered by the gray material, which forms the lunar Mariae. Now then, how about the third rock? What does this tell us? This rock, you'll remember, was the basalt, the dark rock that we find commonly on Earth and is also one of the commonest rocks that's been brought back by the lunar astronauts. Now we know also from the Earth that basalt is also produced by partial molting. It's produced above the in the spreading ridge area in the centers of oceans by the partial molting of whatever it is lies beneath the spreading ridges. And the circumstances or the areas in which we find the basalt on the moon are the very dark areas, these extensive dark areas over the surface of the moon, the so-called lunar seas. Lunar seas because Galileo, who first observed them, thought that they looked like oceans, and therefore the name mare, or Maria, the plural. Now, those basalts are thought to have flooded up into large craters, and therefore the rather circular distribution or the circular shape of the so-called lunar seas. And that stage in the evolution of the moon can be shown then on these two diagrams. First, massive cratering, breaking up the norite, which had solidified in earlier craters. That's thought to have occurred about 3.8, 3.9 billion years ago. And then, into those craters, flooded basalt. Basalt produced by partial melting at considerable depth beneath the surface of the moon, perhaps 150, 200, or even 250 kilometers. That then was the final active stage of the moon, a succession of floods of basalt between about 3.8 and 3.2 billion years ago. And since then, the moon has been inactive. Inactive, that is, apart from occasional moonquakes. And those moonquakes seem to occur close to the boundary between the lunar lithosphere, which is this outer yellow and orange shell, and the lunar asthenosphere. It does seem as though there is an asthenosphere in the moon. You remember that the asthenosphere in the Earth is characterized by some plasticity. It cuts out shear waves generated by earthquakes, and that's the same thing that seems to happen to moonquakes. Here, shear and compression waves are received at the lunar seismic station, but at neighboring stations, the shear waves are cut out apparently because of the presence of a soft lunar asthenosphere. Within that asthenosphere seems to be, we think, a core. So the moon is very different from the Earth, with a tremendous 1,000-kilometer thick armored exterior covering an interior asthenosphere and perhaps core. No jostling of plates is possible on the moon like it is on the Earth, where the asthenosphere is very, very much closer to the surface. So the moon is a very different body to the Earth, but it tells us a great deal about the Earth. It tells us about what might have gone on the Earth during the early stages of the formation of our planet 4 and 3 billion years ago. It also tells us that we ought to be on the lookout for impact craters, and this is where we get back to Sudbury. Sudbury sits on the south side of a structure that looks like an egg cut through. On the center of that egg is Chelmsford. On the far side of that geological egg is Levack. It seems that, in fact, Chelmsford sits in the center of a crater, and the story of the origin of that crater can be depicted like this. Two billion years ago, we think an impact which fractured the rock in the Sudbury area, producing some rock types that we know as the Sudbury breccia and structures that we know as shadow cones. Then, as on the moon, molten material flooded into that crater, and this is the solidified molten material. We've already seen this so-called micropegmatite and this dark gabbro-like rock when we looked at igneous rocks. These two rocks originated by crystal settling, we think, in the pool of molten material. The dark rock is at the base. The light-colored micropegmatite, generally speaking, is higher, above the dark-colored norite or gabbro-like rock. And here, around the bottom of that crater and forming the margins of the crater, is the ore zone that's so very important to Sudbury. Lying above the igneous rock is the so-called Onaping breccia, the rock that the astronauts came to look at, which represents fragmental material that was thrown out of the crater and fell back in and was floated up by this pool of molten material. And then here, represented as the final layer in the crater, is the so-called Chelmsford sandstone, the rather dark, dirty sandstone that forms the rock in the Chelmsford area. That was deposited in what is unique to the Earth, in a water-filled crater lake. We don't find the equivalent of that water-filled lake on the moon, but nevertheless, the story seems to be similar to that, which was we've learnt from the moon. And then finally, the crater was broken up by these fractures about 900 or 1,000 million years ago, those fractures being produced by the mountains that were built along what is now Highway 69. And we look at the roots of those mountains, which have been eroded away. So the Sudbury Basin seems to be something of an analogy to what we see on the moon, a similar structure to the lunar craters. Not as big, but certainly not small in comparison even with a crater like Copernicus. Some remnants of it left because the crater was quite large and has not been totally destroyed by erosion. But just to end where we began on a note of controversy, there are those who believe that the Sudbury Basin had quite a different origin, a volcanic origin. And we can see that on these diagrams. There are those who believe that the Sudbury area was once covered by a very large volcano, that volcano being quite active, but at one stage becoming blocked, the lava in the vent solidifying. And because of the tremendous buildup of pressure in the volcano, remember it's gas which produces the violence and the propulsive force for volcanic explosions. Because the lava solidified in the neck, gas pressure built up in the magma chamber beneath the volcano. And that gas pressure was released in a tremendous volcanic explosion, depicted here by glowing gas clouds of fragments. And that at this stage, the volcano then began to fracture, and that succeeding the eruption, the blocks of the volcano subsided to produce a basin structure, a shallow depression we now know as the Sudbury Basin. So the Sudbury Basin is also a subject of controversy, very much like the lunar craters